In this lesson, we're going to look at linear and angular speed. Now, when you think of the speed of an object, you're probably thinking by default about its linear speed, or the speed that it is moving in a straight line. For an example, say we have a person who runs a distance in some amount of time. And let's say that they ran a distance of 10 meters, and then it took them 5 seconds to run this distance. Well, what we could do is we could break this down and try to figure out, well, how far did they run each second? And if we did that, we would realize that we would need to break into 5 equal parts. So we would have 2 meters, 2 meters, 2 meters, 2 meters, and 2 meters. And every 1 second, we would run 2 meters, giving us a total of 10 meters over 5 seconds. And this is how we tend to think of speed in this linear sense. If you're going in a straight line some distance over some time, you would have a linear speed. So we would say that our linear speed here is 10 meters per 5 seconds, or subdividing down, we get 2 meters per 1 second. Okay, we usually like to have our speed as some distance per unit time. And what this per unit time is referring to is per 1 time unit, whatever we're choosing here. So in our case, we're interested in seconds, so we want to know per 1 second, or per second, right? But you have a car that goes in a speed of miles per hour, or kilometers per hour, or whatever. Our unit time there would be 1 hour. So we typically like to express our speed, our linear speed, as being some distance over time, and we want our time to be per unit time, whatever time we choose to select. Now, that's linear speed. But there's another type of speed that we can have, which is going to relate to what we've been covering so far, and that is called angular speed. Okay. And angular speed is going to basically be a speed of rotation, or how fast our angle is changing. And so remember that we think of angles and we compare to some fundamental unit of 1 turn. So relative to 1 full turn, okay? And now we might choose to call that turn 360 degrees. We might choose to call that turn 2 pi radians, or we might call that turn 12 hours, or we might call it 8 Miller units. But the point is, we tend to think about angles and rotation relative to 1 full turn. So now let's take an example here. Let's say it takes 6 seconds to complete 1 full turn. So I take my pencil and I go and say this took me 6 seconds to make it all the way around in 1 full turn. Okay. Then we would say the angular speed is going to be, and let's do this in degrees for a minute, 360 degrees divided by 6 seconds, which is equivalent to 60 degrees per 1 second. Okay, we remember unit time, 1 unit of time. So that means if we go 6 seconds to go all the way around 1 full turn, we are effectively going 60 degrees per 1 second. And we're able to subdivide, it's not 60, right? 1 second, 1 second, 1, 1, 1. Just like we were able to subdivide our straight line into 5 equal parts for 5 seconds, we can take our turn and break it into 6 parts over 6 seconds, and then realize that it's 60 degrees per second. We could also do this in radians. So we could do 2 pi radians, represents 1 turn divided by 6 seconds, which would mean that we are doing 1 pi over 3, or 1/3 pi radians per 1 second, okay? Or 1 pi radians per 3 seconds. If we wanted to get fractions up top, we could say 1/3 pi radians per 1 second unit time. Or you could say, well, I don't know, that's fine. You get the point. Or if we wanted to do it in Miller units, right, and we called it 6 seconds, we could say we go 8 Miller units in 6 seconds, which means that we go 8 divided by 6, which is the same as 4/3 Miller units per 1 second, or 1.33 Miller units per second. So that's all good and well. That's what an angular speed is describing. It's saying, what is our rotation amount, or how fast is our angle sweeping through rotation per unit time? So it's very similar to linear speed in the sense that you're interested in some distance per time. Linear speed, though, we are moving in a straight line, whereas angular speed, we are describing a turn, a rotation around some center point. And it could be a line that's being turned around. It could be a point on the edge rotating around. It just somehow has angular speed. Okay, so linear and angular speed can be related, but there's something I want to note first. There's an interesting but. Okay, so imagine a rotating record, or CD, or a donut, or whatever is going to help you out here, that looks something like this, right? Basically, the point is it's like a disc, okay? And let's say there's a point on the circumference of the disc. We'll call it point A. Let's say there's a point right on this inner piece of the disc called point B. And let's imagine that as this rotates, A and B must be rotating together. Because if they weren't rotating together, like say A went here and B was still here, well, the disc would have to break apart, or would have to somehow, I don't know, something would be a little weird there. So we imagine that A and B have the same amount of rotation per unit time. And that means that A and B have to have the same angular speed, okay, to be spinning together on same disk. Okay, they have to have the same angular speed. You might think it would take A longer because it's on the outside of the disk, but it doesn't. They rotate at the same speed. And actually, no matter where you are on the disk, you're going to have the same speed. So we can say, so, this is an important so, angular speed is constant on the disk. So if we say that A, let's say that A has a speed of, I don't know, we'll call it 1 radian per 1 second. Guess what B's speed is? 1 radian per 1 second. Okay, so if A's speed is that, well, then B's speed would also have to be that. And if there's some point C, well, guess what C's speed is? 1 radian per 1 second. But where this will get a little bit interesting is in the relationship between angular speed and linear speed. So even though they might seem a little different, angular, we're going in a circle, linear speed, we're going in a straight line, there is a way to relate the two together. Okay, so let's imagine that we have a wheel. And let's say that this wheel is rolling down the road, and let's put a point on this wheel, point A. Let's say this wheel rolls all the way 1 full turn. The wheel rolls down the road 1 full turn. and we end up back where we started, and that same point is on the bottom A. Okay, so 1 full turn, roll down the street. Well, let's say that took us 10 seconds. Let's say it took 10 seconds to get down the street. Okay. The interesting thing here is our angular speed. And let's just do it in degrees for a minute, would be 360 degrees of rotation to get A all the way around, right? Took A all that time to get here. So we would say it was 360 degrees over 10 seconds, or 36 degrees per 1 second. But we could also come up with a linear speed of point A, or just the circumference of the edge of the wheel in general. Because notice how the wheel has rolled. We've gone some linear distance. And that linear distance will be related exactly, in this case, because we've done 1 full rotation, it'll be the length of the circumference of the circle, because the circumference is rolling along the ground. And so let's pretend we have a radius in this case of, let's just say 2. Actually, let's say 3. Say our circumference is 3 meters. Okay, big wheel. Well, that would imply that our radius is 3 meters. That would imply our circumference is 2 times pi times 3, or our circumference is 6 pi meters. Well, if this whole wheel rotated along down the road, but it actually only rotated 1 time as we went down this road, well, that means that this length has to be 6 pi meters. So linearly, okay, we would have gone 6 pi meters in a straight line over 10 seconds. Now, dividing by 10, we would get 0.6 pi meters. So let's just write it like this. 0.6 pi meters per 1 second. So we were able to get between an angular speed and a linear speed, and they're kind of linked by the circumference of the circle, or I always like to just refer back to the radius, because from the radius we can get the circumference, but the size of the circle is going to link us between the angular speed and the linear speed. Okay, in another sense, and I'll show you some animations and some different ways of sort of seeing the relationship between the linear and the angular, but a wheel rolling is sort of the most basic one. Now, let's say, for example, we had a different wheel, and let's say that this wheel has a radius of 2, okay? And let's say that there's a point on the edge of this wheel, and it could really be anywhere. Let's put it up top, and let's call this point C. Actually, no, let's call it point M. And then let's put another point on our wheel. So let me there's our tire. Let's say there's some other point here, and let's make this point B on our wheel. And let's say our wheel is rolling down the road, and we go some distance. And so say our wheel rolls, roll, and we do, let's say 2 full turns, 2 full turns of our wheel, and we end up back in our same position. So our wheel looks a little something like this, still with a radius of 2. Point M makes it back to the top, and point B makes it back to the top, which is quite delightful. Now, point M covers a distance from here to here. As does point B. Now let's look at an interesting fact about linear speed. If I have a disk. And let's call this disk, and let's say it has a radius of 10 centimeters. And say on this disk I have a point, and that point is located such that it is 5 centimeters from the center of the disk. Well, we said a moment ago that the angular speed on the disk as the disk rotates is constant. Okay, so if I denote some point A to exist out here and some point B on the inner ring, well, the angular speed of A, using this omega A, is equal to the linear speed of B. This just means sort of notation for angular speed. Okay, so those angular speeds are the same because as this disk is rotating around, all the parts must be rotating together. Logical enough. Now let's say the disk is rotating at, let's do radians this time. We'll do 4 pi radians per second. Okay, so that represents 2 full rotations in 1 second. So if we want to know the linear speed of A based on this angular speed, well, the linear speed of A can be thought of as taking this circle and point A, and we can imagine that A is going the distance all the way around this circle, and if we turn that distance into a straight line, sort of like unraveling our circle, we'll see that it is just the circumference. Okay, so A goes all the way around once, and then it does it one more time. So A does 2 full turns, 2 full rotations in 1 second. So that means it does the circumference, and then it does the circumference again in 1 second, all over the time increment of 1 second. And so if we wanted to know the circumference of the circle that contains point A, well, we know the radius, so the circumference is going to be 2 times pi times the radius, but we know the radius to be 10, so the circumference is 20 pi. So A is going to go around 20 pi units, and then it's going to go around another 20 pi units, and in total, A, the point A, will have a linear speed of 40 pi, our unit, I guess, is centimeters per 1 second. So if we take that speed that A is going around and around and around, and we turn that into uncurled into a straight line and make it linear, A is actually covering a linear distance of 40 pi centimeters in 1 second. Interestingly, if we do the same thing with B, so here's B existing on the inner circle, and B's inner circle has a radius of 5 centimeters. But the same thing is happening to B. B is undergoing 2 full rotations in 1 second. It has the same angular speed. The angular speed is constant. So that means that B goes around 1 time in half a second, and then around another time in the second half of the second, for a total of 1 second. And so if we unwrap B's circumference, if we go around once, that is like going 1 circumference. Okay, and then if we go another time, it's like going around a 2nd circumference. And so we end up with 1 second, we go 2 circumferences around B's inner circle, because that's the path that B is tracing. And so the circumference of B, or the circle that B lies on, is 2 times pi times 5. In this case, the circumference ends up being 10 pi. So we go 10 pi in the first half second on the first rotation, then 10 pi in the next half second, completing 1 second, 2 turns. And so we go a full distance of 20 pi. So the linear speed of B is 20 pi centimeters in 1 second. And I bet you're thinking, well, look at that. The linear speed of A and the linear speed of B are different, which is a very important thing. So angular speed on a rotating disk is constant. Okay, so if you were rotating and you're on the same disk, or even if you're on, like, say, this arm and this thing's rotating all in a circle, your angular speed is constant. You're going the same degrees or radians, or same degrees, radians, more importantly, same number of turns per unit time. But what is different is the linear speed is bigger the farther from the center you are. Okay, and think of that as, like, maybe you know about running around a track, how on a track it takes the person running around the outside a longer distance to get around. So to make up for this, tracks will have the person on the outside get a head start compared to the person on the inside. In terms of a distance head start, they'll start out in front because it's actually a longer path that they have to follow in total. And that diagram's not necessarily perfect. Oh, I think actually with tracks, you have to go all the way back and you both cross at the same finish line. So they end up having this extra distance right here to make up for the fact that this path is actually longer all the way around. Okay, so linear speed ends up having to be bigger the farther from the center you are, with it being biggest or greatest magnitude on the very edge. Okay, so those are some key ideas from this lesson. It takes some thinking and getting used to play around with this idea, but that's sort of the essence of angular and linear speed and how you can convert between them. Linear speed and angular speed themselves are simple, but the way they work together takes some practice, takes some thinking about, so I highly encourage that you do that. Think about how the path that you follow around the circle can be uncurled into a distance of a circumference. And then that's sort of the key of how all this comes together. One turn equals one circumference. One turn, which is kind of like an angle, right, equals one circumference, which is a length, or it can be thought of as a length. And that's sort of the key between converting between linear, how far did we go, over some angle. So I hope you enjoyed this video. Thanks for watching.